Hi, everybody. Thank you. I want to welcome everyone to our second distinguished lecture of this academic year. It's an honor to be able to introduce Dave Patterson to you. Dave received his bachelor's, master's, and doctoral degrees all from UCLA and joined the Berkeley faculty in 1976. He's renowned for a number of a long sequence, really, of just amazing sort of collaborative research projects at Berkeley: RISC, SOAR, SPUR, RAID, NOW, IRAM, ROC, RadLab, and ParLab. I think that's probably going to be it. We'll find out soon. The contributions of these include, of course, research results, also a huge amount of commercial impact, a great sequence of students, just phenomenal students graduated from those projects. And one of the things I've always admired about Dave and the Berkeley projects is there is enough meat in each of those projects for every student to have a piece that allows him or her to reach their potential. So it's really remarkable how those projects are run and the quality of students they produce. Also, these projects have really created a signature for UC Berkeley, a reputation that makes it absolutely preeminent. Dave is a member of the National Academy of Engineering, National Academy of Sciences. He's been president of ACM. He's received the Turing Award, the Eckert-Mauchly Award, the ACM Distinguished Service Award. He's now a one-day-a-week emeritus faculty member at Berkeley and a distinguished engineer at Google. And today, with whatever time remains, he's going to talk to us about domain-specific architectures for deep neural networks. Please welcome Dave Patterson.
Thanks. This is one of my favorite places to visit and come give talks. I visit once every 5 or 10 years here and catch up and all the amazing things going on. I assume you are all appreciative of having the greatest rainmaker in computer science with Ed Lazowska here, the fact that we're sitting in the second building that he has helped raise, where many of us are looking forward to the first building. But it's really a fabulous space, and it's fun to see here. So what I'm going to talk to you about today is we're in a very exciting time in computer architecture. Is that what computer architects do is try and make things go faster for less money for some workload. And this ending of Moore's law and Dennard scaling has made the general purpose microprocessors not so fruitful, so we're switching over to domain-specific architectures. And basically, they do just a few things really well, but they can't run arbitrary C++ programs, which was kind of the goal for the last 40 years. And so the things we've learned and the experiences may not translate to this domain-specific architectures. So that makes it fun for researchers and engineers, kind of scary if you're at a company. So I guess 6 years ago, Google started doing domain-specific architectures for what was then a new idea of deep neural networks. And the deep neural network model that transforms inputs via calculations of weights to produce the desired output. And the two big things are training, where you kind of develop a model, and then inference or serving, where it uses that training model. The resulting Tensor Processing Units, or TPUs, were first deployed in data centers 4 years ago. If you use Google, you are using TPUs for searching or for ads or for translation. So this talk is going to talk about the first 3 generations of TPUs. So we've talked a lot about the first generation of TPU. I'll talk a little bit more about it today. But the next 2 TPUs haven't been published yet, so this is brand new information. But what I'm talking about is the cloud, not the edge. I mean, the edge is a very exciting area for machine learning. That's just not what I've been working on at Google, and that's what I'm reporting on. So it's based on 2 talks that are both going to appear in Communications ACM. The one that's already appeared, that was on the cover, almost more than a year ago. And this next one that's going to appear sometime in Communications ACM. And this is the part that's not been published yet. So you'll hear about it first. So I think Jeff probably came, when Jeff Dean was the guy here 2 years ago who founded Google Brain, where I'm working. He's the guy who made this observation. I think deep neural networks are going to start at work. If people started using Google Translate on their phone 3 minutes a day, and say 100 million users did that, Google would have to double their data centers. And even Google can't afford to do that. And even if it could afford it, it would have taken years to double the number of data centers because you got to build buildings and stuff like that. So they started this emergency project. And I don't know if they arbitrarily picked the improvement of total cost of ownership for this inference phase by a factor of 10, but that was the charter. So they started this emergency project thinking the DNNs were going to work. And in 15 months, they came up with everything, the architecture, the software stack, the hardware, and deployed it in just 15 months. And this is TPU v1. This is what it looks like. It's a, here's the chip, and it's on a board that's kind of this big, and you can put 4 of them into a server. That's the accelerator. And the heart of the CPU is the matrix multiply unit. Amazingly, 65,000 multiply accumulate units on this chip. So why is that amazing? Let's see if this works now. All right. That's like 25 times as many as you'd see in a GPU of the time. So many more arithmetic units there. It also has a lot of memory on chip. And that is like 4 times as much memory on the chip. So that's kind of the big pieces of why it's a domain-specific accelerator. And then it also had a kind of a modest amount of slow DRAM that was connected. That's where the weights were kept on this design. So that's the big ideas there. That's what it looks like on the inside. And here's what the floor plan of the chip looks like. And more than half of it is for the memory and for the multiply accumulates unit. So most of it is in the parts that are delivering on on the performance that it wants. And then one of the ideas that they kind of resuscitated from the past was 40 years ago, Lyserson and H.T. Kung, who were at Carnegie Mellon at the time as part of Lyserson's dissertation, invented this idea they call systolic arrays, that if you're going to do a big matrix multiply, normally what you do is write the results in the registers and read it back out and write it. You do lots of register accesses. Their idea, you can kind of choreograph the partial products if you're doing a lot of them so that one would just show up at the inputs just in time, and you would save all those register reads and writes to do that and save a lot of energy. So that idea got brought back from the past and used in the systolic array. What it led to is a really amazing resulting in performance. So like, this is for products, not like research papers, but the performance per watt, and with the end of Dennard scaling, performance per watt is a very important figure of merit. This is compared to CPUs in red and GPUs in orange there. This is factors of 80 and 30 times better performance per watt by doing something domain-specific rather than general purpose. And not only that, as part of this first paper, we said, well, this was done in a rush. Suppose we had more time. Suppose we could have made the clock write faster, or made the matrix multiply unit bigger, or made the memory faster. Well, that was the key. That was the memory was pretty slow that had that weights in it. It was a standard memory. Suppose we'd use the graphics DRAM like GPUs used. How much faster would it have gone? The memory bandwidth would have gone up by a factor of 5, and a lot of the applications were memory bound, limited by the memory. And so it shot up again. So it'd be a factor of 7. If we had built that one, it would be 70 times the performance per watt versus GPUs are 200 times. So that's amazing kind of numbers here. So why? Well, probably that giant multiplier with, whatever it was, 25 times as many multiply units there. And not only was it a giant multiplier, it was doing things in 8-bit integer arithmetic rather than 32-bit floating point. So that's much more efficient use of the memory and the computation. This systolic array idea brought back from the past that probably cut the energy costs in half for the multiplier, which is a lot of it. And then it was domain specific. So a lot of the things that are complicated and area consuming on CPUs, like branch predictors and caches, CPUs are covered with caches, they're not there because they're not helpful for this application. It was better to use more multiple units and dedicated memory units. So that saves energy and you could reuse the resources. So that was a big success. So then, while they were getting it rolling into the data center, they decided, what are we going to do next? The original plan was, let's do the next inference. So that's what they seriously considered. We know how to make it better. We've done this other one. But they decided instead to do for the harder training project. And so I'm going to explain, why is training harder? Yeah, but they said, we've got inference working. Let's go for the training step next. Because a lot of what Google spends a lot of its resources on training. So kind of classically, there's a neural network has an input and these stacks of layers, right? And so the way this works, kind of amazingly enough, is you're going to do this supervised model where you start off with the weights set to random initial values, random data, and then you have this labeled data, millions or billions of these pairs of input and results. Like here's an image and it's a cat, or here's a phoneme in here, here's a waveform and the phoneme it represents. So you got to start off with this labeled data. Now what you do is to learn the weights, you use this old idea of stochastic gradient descents, and you do these 3 steps repeatedly. You grab an input result pair, and you run it forward through those layers and see what the result is. Well, since it was garbage to begin with, random data, the first time through it's going to be a crazy result. But then you look and see what the error was, and then you run it backwards through those layers to try and adjust the weights so you can get the right answer. So you calculate the loss function, and then you update the weights. So a key part that'll come later, these kind of updates are pretty small, right? You're trying to adjust the weights eventually so you get the right answer. And then you just keep doing this, millions or billions of times to be able to adjust those weights. And remarkably enough, you start off with random data, you do these label sets, you do this enough times, and it can be smarter than a human at something. What an amazing result this is. So the inference part, the serving is really just the first step. That's going forward through it. You've already got the weights, you go forward. So inference is 1/3 or less than 1/3 of the work. Training's got to do everything else. So why? What else? So a lot more compute. You got to do the back propagation, and it requires you to do derivatives. The activation functions that you do after one of those layers is transcendental, and you have to do multiplications by transpose matrices. So lots more computation for training. It's more memory. You've got the weight updates, and then you have to you have to keep track of information between the forward pass and the backward pass, and that can be 10 times bigger than the weights. Because the training algorithms change, it's got to be a little bit more programmable, because you want to make sure you can handle changes in weighting. Training changes, and it still works on your computer. Tiny integers aren't going to work for training. It's got to be floating point, and it needs to be wider than 8 bits. And then the parallelization between the chips is harder, because for inference, they're all independent. You've trained it, you can just run it through. But you've got to coordinate the weights to keep the weights consistent as you update them. So it's a more difficult computing problem. So 2014, when it started, what did the world look like? Well, people were doing all this stuff on CPUs, and they divide the CPUs into 2 pieces. There were the workers that would do the stochastic gradient descent, and the parameter servers would do the weights. So it'd be a big cluster. The stuff could be flying back and forth, and the parameter servers would handle the updates. And that's the way that was done. It was called asynchronous stochastic gradient descent because you're dealing with clusters and long latency. That's the way it was done. So then became the question for the Google engineers, what are they going to do? Are they going to just do what they did for inference, was just build this cluster of servers that have these accelerators stuck inside them and use data center networking to connect them together? Or are you going to build a supercomputer? And so part of the calculation was, well, how long do these things run? So the Google production applications to train would take between 2 months and 16 months on one chip. 16 months to train. So if you're a computer architect, you love people like this, right? you hate people who say, why are you building faster? My laptop's fast enough. You hate people like that. But people like, it takes me months on a computer to train it, so you like those guys. So they want it, clearly you don't want to wait months. So you want to use hundreds of chips. And the other kind of machine learning conventional wisdom then and now is the bigger machines, the more data, the bigger ML breakthroughs. So the Google engineers decided we're going to build a supercomputer. We're not going to build chips that you stick into clusters and somebody else does networking. We're going to build a supercomputer. So, and that was a really great decision in 2014. This paper that was done, blog post by people at OpenAI in San Francisco, calculated over the next 8 years how, for the state of the art, the bleeding state of the art, how much did compute go up? And they said it was doubling every 3.5 months, and if you multiply that out, that's factors of 10 per year. So if you wanted to be at the bleeding state of the art there, you would need 10 times as much compute every year, so which is amazing. So yeah, so people really wanted supercomputers for training. So the critical feature of the supercomputer is the way they talk to each other, or the chips talk to each other. So Google invented something called ICI. It's a custom intercore interconnect that they did custom for this design. It's not some standard that you buy off the shelf. It runs at about 500 gigabits per second in both directions per link, and there's 4 of those links. And then rather than having a separate switch, they all through the switch is distributed through all the chips is a kind of a standard way to build a supercomputer. And it turns out one of the nice features of building a supercomputer for domain-specific architecture is you know the communication patterns. The challenge for normal supercomputers is, well, there's all kinds of ways people might communicate. How do you balance that? But you're doing this weight update thing, and you can map that really well on a 2D torus. And that's a nice, simple topology for things to connect to. So we can do a domain-specific topology for a domain-specific supercomputer. And that's what a 2D course like is. It's just a matrix, and you connect the ends. That's pretty easy to build and deploy, and it's very economical. So you do direct wire connections between the TPU chips. On the die size, which I'll show you, it's about 1/8 of the chip is all you need for doing those links. That's the extra cost. And it saves power and makes it easy to build these things. That's the TPU V2 there, and those colored wires are the wires that connect them together. But they're basically adjacent links, except for the round ones, the ones at the ends. And then the link bandwidth is, this is 500 gigabits per second. That's like 5 times the link bandwidth over what was available in 2015. And it's probably, let's say, 1/10 of the cost, because you don't have to have the network interface cards, you don't have to have the switches, and you don't have to have a little protocol engine that runs that. So it's much simpler design, and so faster and cheaper. And then this thing happened once the hardware people said we're going to do this really fast supercomputer interconnect. That led to innovations in the algorithm. Because it was a dedicated network, there would be no kind of variability in the latency like there are in clusters, so you could do synchronous parallel training. And so instead of having parameter servers and workers, and you have to handle asynchrony, you could just get rid of the parameter servers. They have the parameters as well as doing the SGD, and there'd be long short-tailed latency, so you could keep everything synchronous, which led to a better designs. And it means, as we'll see later, given that you could do all your work synchronously, you get really tremendous speed up as you add chips to it. Okay. Then the next question is, okay, so we did the network. That's the big question for supercomputers, the network. What about the chips themselves? Well, then one of the questions was how many cores per chip. On TPU v1, we had 1 core per chip, so that's attractive. But as Google went to a more aggressive technology for TPU v2, with the shrinking feature size, the wire delay increases relatively. So what's the right number of cores per chip? Well, we know training can use a lot of computers, a lot of processors, because it takes months to run. But so how many cores should we do per chip? So we're building a supercomputer. We went to Mr. Supercomputer, Seymour Cray, for advice, and this was something Seymour Cray said. If you were plowing a field, which would you rather use, 2 strong oxen or 1,024 chickens? So we followed his advice and went with strong oxen. So there's 2 tensor cores per chip. And a big reason was we could, that was pretty efficient, and we could. It was easier to program it for 2 cores per chip than lots of little cores per chip. So that's the way we went. Here's what the block diagram looks for the TPU v2. It does have a matrix multiply. It's a smaller matrix multiplier unit, so it's 1 per TPU. For TPU v2, there's also a unit that does transposes, permutes, and reductions, so special hardware for those kind of matrix operations. There's a vector processing unit, which does 2-dimensional vector processing, and it has a vector memory as well. And its peak performance, this thing is where it gets the highest performance, given you have 32,000 multiply accumulate operations per second. Whereas this one has about 1/10 of that peak performance. This thing fetches instructions from memory. And then the ICI I already told you about that connects the chips together. And then one of the weaknesses of the TPU v1 was that memory system, the standard using standard DRAM instead of graphics DRAM. Well, they didn't want to make the mistake this time, and they went to something that's called high bandwidth memory. And what high bandwidth memory is a more novel packaging solution where you have a substrate that's called an interposer that you put your TPU v2 die on, and then near it are short stacks of DRAM at very wide interconnections. It has amazingly enough, 32 64-bit buses per one of these tensor cores. So there's two. So they actually have 64-bit buses per chip, whereas a server might have 4 or 6 of those 64-bit buses. So it has 20 times the memory bandwidth of TPU v1. So they weren't going to make that mistake again. And then this is an accelerator. It talks to the host CPU over a standard bus. And again, it's typically about 4 of them per server. This is what the floor plan looks like. I said the ICI links, which are in these corners, use up a small fraction of the chip. There's also some ICI switch stuff in there, but it's about 1/8 of the chip. And even the matrix multiply units you see aren't all that big. Now, when you're doing domain-specific architectures, kind of the scary part about it, and what people worry about, especially people who would rather use FPGAs than ASIC chips, is like, what happens if the algorithms change? Then things doesn't work. So this happened during the design of the TPU v2. Is in 2015, when they were building it, this new algorithm appeared called batch normalization, and it could speed up training and make it more accurate by factors of 10 or 14. So essentially, what it does is it subtracts out the mean and divides by standard deviation to make it look like samples of a normal distribution. That led to this big advance. So, TPU is an instruction set, it has software, so you could do it in software. But it ended up with a lot more vector operations. And our vector unit at the time when we were doing it wasn't all that powerful. So they made the vector unit 8 times as powerful, so 8 times as many what they call vector lanes, to be able to do a lot more computation of the vector unit, which would be needed now because of batch normalization. So that's an example of something that's done. In terms of the instruction set itself, it decided to go with what's called very long instruction word model. So you can specify instruction word parallelism on an x86. They try and guess by looking at the instruction stream. The very long instruction word model is you do it statically. This is a 320-some bit instruction that has actually 8 slots for operations. So in one instruction, it could do 2 scalar ALU operations, 2 vector ALU operations, 1 vector load, 1 vector store, and then queue something for the matrix multiply unit and queue something for transform unit. So you can do 8 things potentially in this one very long instruction. So that's going to be a compiler challenge to be able to figure out how to use it. And then here's the amount of memory that's the state per tensor core. And one of these things, the big part of this is the vector memory, which is 16 megabytes per tensor core. So there's 2 of them on the chip. OK, now I showed you in the beginning for TPU v1, we said, well, here's this emergency design. What about if we did some variations? What would happen? Well, we're going to do better than that this time. Rather than a hypothetical TPU v2 with different types of memory multiply units and speeds and stuff like that, Google actually built 2 chips out of the very same technology. So the TPU v3 has basically a third faster. The clock is a third faster. The ICI interconnect bandwidth is a third faster. And the HBM memory bandwidth is a third faster. But instead of having 1 multiply unit per core, it had 2 multiply units per core. So there's 4 in the chip. So when you multiply that together, it has 2.7 times the peak operation bandwidth on this design. How were they able to do that? Well, it burns a lot more power. Well, how could they handle that? Well, they went from air-cooled design to liquid-cooled design. So, and I'll show you that in a picture. So instead of just dumping the heat in the air and having air conditioning units suck that out of the air, you heat up a liquid which can be more efficient. It has more DRAMs in that HBM stack, so it has more capacity. And they decided to scale up the size of the supercomputer by a factor of 4 that they're going to build. And then it's 2 chips in the same technology. How much bigger was it? Well, because they already had a good idea of what the layout challenges were from TPU v2, it was only 6% larger because it was a much more efficient floor plan. So do all of that. And here's what they look like. And Jeff Dean probably showed these. So this is TPU v2, and you can almost see that this is a heat sink, and that heat sink is like this tall, right, on that board. And this one has 256 chips and then plus some room for I/O devices. Here it is with the liquid cooling, and you see it doesn't have this is very flat, but because and these pipes, liquid are going through these pipes, and this is copper to help cool it down. So the water, or whatever that liquid is, flows through that and comes back out, cold in and heat out, and that's how they cooled it. And now we can go 8 of these racks, which has 1,024 chips in it. And so this is, to keep up with the OpenAI challenge of factor of 10 in 1 year, this is a factor of 10 in 1 year. So OpenAI guys would say, okay. But it's a pretty amazing thing to do. That's the peak performance. Okay. So now what are some of the features of these things? This is TPU v1. And again, this clock rate is, that's the same clock rate as v2, and it was a third faster for TPU v3. And then here's the Volta GPU, which is the latest GPU, which has much better technology and a much faster clock rate. They're in a much better technology, the so-called 12 nanometer. Google doesn't reveal, its partner's technology, but it's a much older technology. V1 was in an even older technology. It was less than half of the competition then. This is less than 3/4 of the competition. This is 6% larger. So it's a smaller die and an older technology. And then architecturally, I'll talk more about that later, but you see this is a modest number of cores per chip, and the GPU is in the many cores per chip model there. Okay. Now, I'm genuinely surprised as part of my career that I'm going to talk about somebody who doesn't use IEEE floating point arithmetic. So Berkeley is very proud of the IEEE floating point. Velvel Khan won the Turing Award for his contribution to IEEE floating point, and I never thought I would ever talk about a chip that doesn't follow IEEE floating point. So let's talk about that. So TPV2, the systolic array, 8-bit integers, that was a big win. So could we do it again? But 32-bit floating point ALUs are tremendously bigger areas, so that seemed unaffordable. And by the way, 16-bit floating point is much faster. If you were looking at that last chart, 16-bit floating point is like 8 times faster for both the GPU and the TPU than 32-bit. The multipliers are much smaller in 16-bit than 32. So they started playing around with the floating point formats to see if this narrower floating point would work for training, right? That was the test. So what they found immediately is the outputs of the matrix multiply unit and the internal sums need to be remain 32-bit floating point. Otherwise, things went to hell pretty quickly. But if they followed the IEEE standard, which is shown here in the slide, as you see, the exponent, it's only 16 bits, so the exponent is only 5 bits. If they did that, quickly accuracy went down. And if you're a machine learning researcher, accuracy, which is how good your model does a job of recognizing images and labeling them, that's everything. They care passionately about accuracy. And if you cut accuracy like 0.5%, they're going to yell at you, right? So if you're going to 16-bit floating point, it's much faster. But wow, it hurt accuracy a lot. If you think about it, 5 bits of exponent can't even represent a 32-bit integer number. If you took a 32-bit integer number and converted, it wouldn't fit, right? It can only a 5-bit integer can only fit something about 60,000 in integer. But if they cut the mantissa down from 23 bits to 7 bits, it still worked. So this is one of the claims about, as I learned about machine learning, is they're saying, it's low precision linear algebra. And it's like, well, okay, how low can it be? This is an example of how low it could be. They could cut the mantissa from 23 bits to 5 bits, but the range was really important. So Google invented this format called Brain 16 format that is not IEEE. And the saving grace was that by keeping the exponent the same size, they'd have exactly the same software behavior, right? If you know what nans are and the infinities, they would occur at the same place because the exponent was the same size and encoded that way. And this was enough precision to be able to do a machine floating point. So why is that a big deal? because you think of it, you'd think it'd be the 16 bits is the area, but it's not. It's the mantissa. It's the fraction piece of it that you're doing the multiplies. So the smaller the fraction, the smaller the area, the less energy, and it's much more economical to do that. So this shows that if it was 32-bit floating point, it'd be 9 times the area and energy of brain float floating point, and the IEEE standard would be twice as big. So these factors of 2 is a big deal for something when you have 65,000 multipliers. And then it was easier for software. It was easier for hardware, but then because of this narrow range, if you're trying to make 16-bit floating point work this narrow range, you've got to modify the software so you don't turn things into underflow. So there's this idea that that NVIDIA uses called loss scaling, where you have to scale the software to make sure you don't lose those bits. So it's extra work. Intel did a recent study that corroborates that benefits. They might not have mentioned that Google invented brain float, but they said they still call it brain float to do that. And then so it's this rare thing in hardware where here's something that's easier for software and saves energy. You have this trade-off. And so this is an idea that has caught on, right? Is that Google has had it in data centers for 2 years, and people have now found out about brain float. It was in TensorFlow, so it wasn't like you couldn't learn about it. But so now ARM, Intel, and lots of startups have announced that in the future they're going to use this non-IEEE format going forward. Okay, so that was the supercomputer interconnect and the supercomputer nodes and the supercomputer floating point. What about the compiler? So this is all about performance. So you would think, or I would have thought that something based on Python, like TensorFlow, which is it's a domain-specific library on top of Python, that's got to be slow, right? It's Python, right? Python's famously slow. C++ is fast, right? You'd think how is this going to work? Well, TensorFlow has, it's kind of a program that creates these graphs, right? But for these programs, multi-dimensional arrays are first-class citizens. So what this means is, first, you can operate a multi-dimensional arrays explicitly in TensorFlow, unlike in C++, you've got these nested loops that are representing some, and you have to reverse engineer that, and compilers are not good at figuring that out. Secondly, they have explicit analyzable and bounded data accesses. You know exactly what's memory is being accessed, and that's really hard to figure out in C++, which has pointers and stuff like that. And there's no aliasing, unlike C++. So ironically, or to my surprise, TensorFlow is much easier to get performance out for these multi-dimensional arrays for low-precision linear algebra than C++ is, this language that, that people have used for performance. So this allows the compiler that the supercomputer uses to do all kinds of transformations that would be very hard to do with C++ on traditional hardware. So this compiler is called XLA for accelerated linear algebra, and it really, everything happens in the compiler in this design. It exploits the parallelism. There's up to 1,024 chips, 2 cores per chip. It handles that kind of parallelism. There are these 2D vector units, which is a new challenge. So two-dimensional in data in memory and in registers, and you operate them and stick them back. And then there's this instruction level parallelism. 8 operations, 300 bits. Lots of parallelism that it has to be able to exploit. The 2D thing is a new challenge. We've had, since Seymour Cray, we've had one-dimensional vector units. We understand that one pretty well. These 2D things are a new challenge. We haven't had computers that have had this before, and so it's harder to do. And on top of that, the compiler has to manage all the data transfer. There's no caches. There's no instruction cache. There's no data cache. So it's up to the compiler to schedule all the operations and to move the data properly in the design. So it's all up to the compiler. Now there's a classic operation in compilers called operator fusion that's been around forever. And what you try to do is if you're going to do 2 operations back to back rather than write it to memory and read it back, let's see if you can put the operations together and skip that. But now you want to do a 2-dimensional version of that. That's operator fusion. And then, how fast are these things going to improve, right? Is this TensorFlow thing based on Python, is it going to improve fast, or it's newer technology and compilers are going to move faster? I'll talk about both of those. So this is the benefit of going from no fusion to fusion for benchmarks I'll tell you about later. So it's factors of 2 or 3. And the 2 exceptions here are this convolutional neural network and ResNet 50, which is also a convolutional network. And why do they stand out? It's because there's an idea in these deep neural network models of what's called skip connections, where they skip over a layer, and that works out really well if you do fusion. The other thing is how fast are they getting better? So there's this benchmarking effort called MLPerf that I'll tell you about, and this is the Volta GPU in green for their benchmarks, and here is the TPUs in red, and this is just 6 months apart. How much faster did it get? And the GPUs improve. They're a third faster, and the TPUs are a factor of 2 faster. So that's amazing progress from compiler's perspective. If you for C++ compilers, if you made it 20% faster in a year, you'd be a hero, right? So this is tremendous progress because these are much newer stacks. And we found this for the production applications as well, that over time, it wasn't as big in numbers, but over time, they were getting a lot faster. So because it's a newer stack and a newer compiler technology, it looks like there's big opportunities to make improvements. So now that we finally explained to people what TPU v2 and v3 is, and you've always been able to know what NVIDIA's been doing with the GPUs, we can compare them architecturally, these architecture philosophies here. So what multi-chip support, that's a first-class citizen. We were building a supercomputer, so the interconnected network is on the chip, and they plumb the ops all through the compiler and the TensorFlow. For NVIDIA, they do it 2 layers, right? They're accelerators that go into hosts, and then you use standard networking to connect those hosts together, like InfiniBand and InfiniBand switches. So it's 2 different technologies to put together. The multiplier are these big systolic arrays, the 4 of these per chip, where they have many small. They do use systolic arrays in the Volta GPU. They're just tiny ones. And then because they use this IEEE floating point, they have to compensate with loss scaling in software. We do the 2 big oxens, 2 cores per chip, and XLA compiler overlay handles all the overlays in software. With GPUs, they have 80, on the case of the Volta, of these multi-threaded cores. They have so many threads, they have to have 20 megabytes of registers to keep all the threads alive. And then they've got threading hardware and CUDA, coding conventions, to have those overlap. And then the memory hierarchy, there's one big software-controlled scratchpad memory for the TPUs that the compiler schedules. And then when it goes to DRAM, it sets up what are called DMA access to stacks of DRAM, where it's kind of a mixed-up scheme over for the GPUs. They have both caches and scratchpad memories, and then they have all this multi-threading stuff, and they have hardware to kind of unwrap the multi-threading to get sequential performance D-accesses. Okay, so that's high-level comparison of the 2. So just quoting some architects at Purdue, they did an op-ed earlier this year, and they said GPUs incur high overhead and performance area energy due to the heavy multi-threading, which is unnecessary for DNNs, which have prefetchable sequential memory accesses. The systolic organization of TPUs captures the data reuse while being simple by avoiding multi-threading. And so I don't disagree with that. I think it's a fine observation. So besides these architecture differences, the technologies that the 2 companies are using are quite different. NVIDIA's been building chips for a long time. Google's new to the game, and they're behind. So it's a huge chip, what's called a full reticle. You can't build a bigger chip, and it's in a much newer technology. So I tried to adjust, if it was in the same technology, how big the chips would be, and it'd be less than half the size of the same technology. So I'm trying to come up with a cost metric. So that's the blue bars relative to Volta. Then blue and red bars are the 2 generations. Then what about the power? And for a 16-chip system, it's a third or a fifth less power, and that power is correlated with total cost of ownership, so that matters. And then you can rent these things in the cloud at Google, and here's the different prices here. So it's not trying to say this is exactly the number, but here are these 3 metrics are cost-related, are all less for the TPU than is for the GPU. So it's certainly a cheaper chip in an older technology. Okay. Now, what about performance? This is kind of the bottom line for a lot of architects. That's what I'm trying to do. So computer architects grade on a curve, right? They don't grade on an absolute scale. It's not like, okay, if you get 90% of this, it's an A. No, it's what's the competition? because if it's the same era, people have about the same opportunities. So it's not a perfect grading system, but that's the way we do it. So I'm going to split this grading on the curve into two pieces: is per chip performance and then the supercomputer performance against Volta. And why do we care about the per chip? Because if it's wimpy chips, it's like the oxen, right? If instead of oxen we have cats or something, right? I don't care if 1,024 of them, that they're not that fast. So how fast are the chips? And then another question: we're training chip, but what about how well does it do inference? That's for the chip. And then how about the supercomputer? We can put 1,024 together. Do we get perfect linear speed up? Like, is 1,024 chips 1,024 times faster than one chip? How close? That's kind of the ultimate. And then another measure that the high performance computing people typically use will multiply the scale up to how efficiently do you use a chip. And that's a measure that's used because these things cost millions of dollars. Okay, that's the setup. What are we going to run? We have to have fair benchmarks for this. And so the TPU V1 used Google production apps, which was very realistic, but no one else can see what Google production apps are, so that's not very helpful. So I and the people from other places started meeting. So these companies, Baidu, Google, and Harvard, Harvard, Stanford, and Berkeley, and those two companies started meeting, I guess, a year and a half ago, to try and come up with some benchmarks. And that has now expanded to 50 companies and 8 universities to do that. And they did training benchmarks first. They've had 2 deadlines. I mentioned those 2. And now the inference deadline was just a few weeks ago, and the results will be announced next Wednesday. So that'll be interesting to see what happens here. So this is now the probably the standard way that machine learning is going to be measured. And if you're interested in participating, MLPerf is open and would love more people to join and help. To keep the training costs low, they don't take very long to train. Instead of months, it's a day or less to train. So to measure the supercomputers, we have to include Google production applications. So that's why that's included there. So in terms of the types of applications, similar to TPU V1, we have multi-layer perceptrons. This is the classic neural network. Text is input. It's fully connected. All the inputs go to the next layer. The convolutional neural networks, another classic design for which LeCun won the Turing Award, probably in big part for this CNN. So this takes images as input. It does this localized calculation for the next layer. And then the recurrent neural networks are where they bring in sequentialities that they use the previous state as well as the inputs to calculate the next one. And this is typically used for translation and has text as input here. So there's 2 of each of those for the production applications. So in terms of single chip performance, at the top is the MLPerf benchmarks. This is relative to TPU V2. And if you look, they're pretty comparable. So green is TPU V, is the Volta, and red is the TPU V3. So they're both about the same, 1.8 to 1.9 times as fast. Now for the production applications, it's a very different story. Again, the TPU V3 is about 1 times as fast. So that's nice, consistent. But the Volta is much slower. So why is that? A big reason is the Google apps. We know now that we do measurements, nobody at Google uses FP16 on the production applications. They don't try to use it. And so what I would love to be able to do, and I'm pretty sure NVIDIA won't do that, is get performance counters in all the Volta GPUs and find how many people are using FP16. You can do it for benchmarks. NVIDIA is highly motivated to do that in benchmarks because they're 8 times faster. But in the real world, do people use IEEE? Are there people who are using Voltas here? No? Okay. I'd love to know the answer to that. Because is it really just a really great benchmarking technology, or do people use it field? And I don't know the answer to that. But Google certainly doesn't use it. Okay, what about the inference speed? So this is a response time versus inferences per second, so you want to be over here. We're low response time in that. So here it is. We start off for this particular CNN example, and its response time in milliseconds, and how many inferences per second was about 50. When we move it over to TPU V2, Well, that's 5 times faster in almost 1/3 of the latency. Now, it's so much faster that this is faster response time than this application needs, so you can increase what's called the batch size, which is how many operations, how many data sets you do at once, and you can make the process more images at the same time, so you can kind of double performance again. And the latency goes up a little bit, but it's still inside the limit there. And then if you do TPU v3, it's the same inferences per second, but you drop down on the response time. So inference is kind of the first phase, the forward through. So if you do a training chip, you can also do inference pretty well. OK, now the supercomputer stuff. So here's the number of chips, and here's the response time, and this would be perfect right here. So this is for ResNet 50, which is the only one of the MLPerf benchmarks that you can run at 1,000 CPUs or GPUs or TPUs. So there's 3 results. This first one, the gold line, is what was published by Google for ResNet 50 before the MLPerf competition. The blue line is part of the MLPerf competition, so it goes from 3/4 of the chips to half of the chips. So why is that? And it's basically the rules of MLPerf. There's something called evaluation, where you want to see what the accuracy score is, so you run this holdout training set. Most researchers don't include it. And then MLPerf, to deter cheating, makes you do an evaluation at the end of it's called every epoch, every time you go through the data once. And you go through that 10 or 100 times. So nobody would do that, but it's a fair thing to do. And then the green line is for TPU, for GPUs, and they can do 1,500 chips at about 40%. So that's there. OK, so that's MLPerf, so I don't know how important that is. What about the production apps? These are the 2, the MLPs, the classic ones. And they're limited by something that's called embeddings. This is about 40%, which is not that bad for a supercomputer, and this is more like 20%. So embeddings was a kind of one of the big uses of translation is where you take these words and you put them in a vector space and see how close they are and do your calculus there. It's basically very sparse data converted to dense data. Not every DNN uses it, but these 2 use it. And it's much harder calculation because it's doing table lookups and stuff like that. So that was a limit for them. But what about the other 4 applications? And this is, to me, the startling one. This is the best supercomputer scaling I've ever seen, right? CNN 0 is, this is Alpha 0, the thing that was on the cover of Nature magazine. It won at chess and Go and Shogi. And that runs at 96%. And these 3, which are, this is another CNN, and these are 2 translate ones, they run at 99%. Well, wow, that's amazing. What about traditional supercomputers? At the last MLPerf, the Fujitsu people submitted a result on this supercomputer, which has that's how fast it ran. So smaller is better for doing the training. This is how many GPUs and CPUs they use. Now, what they did is, to get that result, they did some changes that you're not allowed to do in what MLPerf calls the closed division. There's a rigid set of rules. There's this other thing called the open division that's more flexible. So this result is in the open division. Had both NVIDIA and TPU done those same optimizations, they would have run about 10 or 15% faster too. OK, now the next thing I did was, well, what about traditional supercomputers? There's something called the top 500 that has been around for decades, fastest at the world at running LinPack. Now, what LinPack does is uses what's called weak scaling. That is, the more chips you have, they synthetically create more data to keep all the chips busy. And LinPack's been criticized for that not being very realistic. That you can just synthetically make your things bigger. And it does its work in 64-bit and 32-bit floating point. We're going to compare that to using Alpha 0 on the TPUs. Now it's using 16 and 32-bit floating point. And then here's the top number 4 on the top 500, that one. And then here's the number 1 in the green 500. The green 500 is you divide the flops by the number of watts you use to see who's the most efficient. And then I threw this one's kind of pretty good in both of them, the Fujitsu one. And by the way, Google's not just building one of these TPUs, right? These supercomputers. They build a lot of these supercomputers. So if we could actually submit these, there would be a lot of spots. So what's the percentage of peak that they're delivering? And here is the TPU v2 and v3, and they're at 70 or 80%. So amazingly, for an alpha or this production application with real-world data, they're at 70 to 80% of their peak, which is even higher than running this synthetic LinPack thing, which does about 60%. In terms of the top 500, that's 87 petaflops that are done on TPU v3. And then for the green 500, it's factors of 5 or 10 in terms of the performance per watt for these kind of supercomputers. Okay.
I couldn't see the legend.
The what? Yeah, the legend. Okay. That blue is TPU v2, red is v3, and then the rest of these are. This is a classic supercomputer, the Tahani. That was number 4. They're at 61 petaflops, and then and the performance per watt goes way down for that one. And this used to be the record, or this is the record for green 500. These are much higher in the performance per watt. Right. Yeah. So this is 64-bit flops, but it's on synthetic data, right? It's weak scaling with 64 bit. So it's nowhere near as a perfect comparison. But it was I was interested to see where it would end up on this thing. And to me, 84% of peak is amazing, at 1,024 chips. And I was just interested in the other ones. So now, let's put in perspective this announcement. So this is Sundar Pichai, the Google CEO, and 3.5 years ago now, we had this kind of like Steve Jobs. Oh, by the way, I thought you might be interested. We've been running in our data centers this thing called the TPU, and it's got an order of magnitude better. You see, this is TPU and this is other, right? And this was at least a factor of 10 bigger than that. And by the way, we did that. And that's the announcement, right? Just kind of threw the one slide announcement there. So this was like an earthquake in Silicon Valley. So the way I think of it now is, if you know Helen of Troy, she was described as, a poet described her as the face that launched 1,000 ships. Helen of Troy was stolen from Sparta, and that led to the Trojan War and stuff like that, right? So this is the TPU v1 is the launching of 1,000 ships, right? So what happens next is Intel starts acquiring companies. Nirvana, almost $500 million there, and then Movidius, another $500 million, and then $15 billion, and these are months apart, and then Alibaba and Amazon have both, within the last 12 months or so, announced their own versions of, like TPU v1, they announced their own custom inference chips. And then there's at least 100 startups who are taking venture capital money and investing in this space. And all the ideas that didn't work for general purpose computers are being resuscitated. So there's an idea called data flow architecture, not the classic von Neumann one. There's a company that's doing that. Coarse grain reconfigurable, that's the next generation of FPGAs. There's a company startup doing that. Asynchronous, why you spend all your time with the clock? That's wasting power. Let's get rid of the clock. There's a company doing that. Analog computing, why limit to digital? Well, let's do the multiplies in analog and convert them back to force. There's a company. I think in every of these cases, there's multiple companies doing these things, but those are ones I know of. And then the most way out there one, and I'm rooting for them to be successful, is called wafer scale computing. So a wafer is the size of a big frisbee. Today in conventional wisdom, you chop it up into die, you put them into packages, put them on printed circuit boards. And this kind of question, why do you do that? Why don't you just make the computer out of the wafer? So that's what they're doing. So they talked about the physical. So they have a wafer. It gets very hot, so it expands. So they have to have a cooling system with water or some liquid that sucks the air out. And imagine all the things that might go wrong with that. You're a startup company and you're betting that you can do wafer scale integration, which many bold people have failed at, and they're going to do that. So this is surely the most diverse time in computer architecture. There's been no era where at the same time there have all these people trying commercially to make these technologies work because of the excitement of machine learning. Most people are doing inference. Most of those startups do that. Only 5 of them I think there's only 5 that are doing training that I know of. And none of them have submitted performance results yet. So it's a very exciting time. We don't know quite what's going to happen. If none of them, if they never submit ML perf results, we'll be kind of suspicious. But all right, so now I got my last 2 slides here. So TPU v1 is, as far as I can tell, had Google not made that announcement, or if they made the announcement a year later, everything would be a year later, right? If everybody who did a start, people would use that to recruit people. People used that announcement to get funding. It was I don't know why they made the decision, but it changed history. This chip, which does 90 tera operations at 75 watts, is still pretty impressive, and it's 4 years old, and it's still being used at Google. Probably it's about, TPU v3 is about the same speed of Volta per chip, but it's got this much better scaling. I still can't believe things at 99% for production applications. Much, different floating point arithmetic, but pretty high performance per watt. I think it was the things I told you about, the interconnect, the systolic arrays, the B-float 16, and being dedicated for DNNs. And it's an older technology. Smaller dies in an older technology, which makes it look like. So thinking about, and this is my last slide before last slide. It's, these DNN models are improving really fast. Their long short-term memory's been around for a while. Then 2 years ago was Transformer that everybody's doing, and now it's BERT, a version of Transformer that's got 1,700 citations in 12 months. Right? What an amazing fast field. Running these things well not only is interesting intellectually, it has huge commercial impact. There's clearly more open problems with DSAs than general purpose computing. It's really, I don't know what the ideas are to make general purpose computing run faster, but there's all kinds of things that might work for DSAs. And you can have bigger impacts with that way. To be a person like me, to work in this area, you got to learn more. It used to be not just, some simulator and spec benchmarks. You got to know much more of the stack, which is, it's interesting to learn that stuff. And so if you like stuff like this, send me email. All right, with that, I'll open for questions. Okay, Michael, I know the name of everybody here, so I'll call by name. Michael.
So you mentioned early in your talk the 12 months training time. And
8 on one chip.
Yeah, and alluded to how you had good scale arrays. I was wondering, how do you partition training across 1,000 chips?
Yeah, so there's the kind of two ways they're called data parallelism. How do you partition over 1,024 chips? So the two ways of doing it are called data parallelism and model parallelism. This is just data parallelism. So there's just enough data that you can just keep all those chips busy. So we haven't had to go to a model parallelism, which is more like classical supercomputer parallelism, where we have to divide up the computation on another axis.
Do you have to increase the batch size to get
Yes.
parallelism?
Yeah. So what batch size is the number of things you operate at the same time. And if you ask, I knew I had a long talk, but if you ask about batch size, oops, here we go. So my colleagues at Google did this paper, Shalu et al., and they looked at how much benefit you could get from increasing the batch size and still get good accuracy scores, because there was questions about that. And it's a 50-page paper where they did it, but they found basically 3 regions: perfect scaling, where you double the batch size, the number of steps go in half; diminishing returns, where you double the batch size and the number of steps go down, but it's not by factor 2, and then no more benefit. And the batch sizes are really big. So if you want to do what Google is doing, you want to have really big batch size to keep your machine full, you like this idea that, wow, batch sizes of 8K to 256 is perfect, and you still can get benefits at 4K to 65K. So this is one of the nice things about being at Google, is that people do research like that. Yeah.
Yeah, so I have a follow-up question. There's another question. So the follow-up here is that if you decrease if you want to have smaller batch size, because then you have better statistical efficiency, right?
Then you have better
statistical efficiency. You tend to get better training with smaller batches.
No, these results show you can get without hurting the quality score, you can have bigger batch size. That's what their results.
So I guess the question is, how do you keep up with network bandwidth, right? Because eventually this problem, aren't you going to be limited in all the bandwidth needed to update the models and then send the updates to all of the other nodes?
Yeah, so I think the way it works is the bigger the batch size, the less you have to communicate. And the smaller the batch size, the more you have to communicate. So for the Cerebrus thing, which has no DRAM on it, they're a small batch size design, so they're going to do a lot more communication, but everything's on the wafer. That's kind of their bet.
Okay. Well, here's a question I really wanted to ask was, okay, so you talked.
Nope, no, it's okay.
Well, you know,
go ahead.
you've been teaching architecture for a long time, right? And now, you know, architecture is just like getting popular again because people.
So I missed my chance, or no?
So how do you think we should deal with needing more and more people to understand hardware and design domain-specific architectures? Because it seems to be the way we're going to rely on to get better and better performance. So how do we?
I think we should hire more computer architecture professors. Yeah, I would say.
It's not sufficient, right? So
I was talking to Magda earlier, and what an exciting field we are in, is that it seems like every couple of years you go, wow, things are really exciting now. I think that is not uniform across all disciplines, right? I think within computer science, there are fields that, without naming names, boy, things are polishing a pretty smooth stone, right? And I think we can say there were periods in computer architecture that were, there's like there were decades in there like, wow, this is pretty boring stuff here. Like, why did I want to work on this area? This is not one of those times. Right now, this is a very exciting time in architecture. So I think in computer science, my guess would be we haven't had a decade that was boring for everybody. I don't think, but maybe there was, and that's when computer science enrollments plummeted. But this is not one of those times. Machine learning is highly exciting. The ending of Moore's law, and this ravenous ML colleagues who need every cycle to get what they need Moore's law to continue, and it's not. And so this is an exciting time for us. So my guess is, within computer science, there are these things that go up and down in excitement, and it's a very exciting era right now. I think it's great that, computer architecture is not everybody doing branch predictors, right? I think this is great.
Designing hardware, so the tools are so, despite their need, they're super primitive. We can't teach Verilog to everyone because it's too boring.
Verilog is awful. Some of us have worked on, some of us have had colleagues that have made taking advantage of more modern programming languages ideas to improve that. I can tell you the people at Berkeley who have learned Chisel, which is an example of that, they're never going back. They're never going to start writing Verilog again. There's practical reasons to write Verilog because there's all these hardware engineers that don't know modern programming language ideas, but we're researchers, right? So I think it's going to be hard to get students excited, and what they have to do is do things in Verilog. I think so. I don't know what the right solution is, but something that they're comfortable with more modern programming language concepts, having Python as their first language, and so we need to do something to raise that level of innovation. And I think we also, this idea that you guys are doing is building chips is exciting, right? And it's the fact that you can get chips back. That's the thing that we have as architects over software people. Their stuff is all in their head, right? Show me your program. Well, it's bits somewhere, right? Or here's a listing, right? Oh, well, that's very exciting. There's chips. You can give earrings to your mom and bracelets, and it's exciting. The chip comes back. Does it work? How power and stuff? It's we're creating physical objects. We've got something going for us too, and we need innovation now. I think how much of the economy is based on computers getting faster every year, right? People are counting on that, and where's that going to come from, right? It's going to be heterogeneity of design, and so this is going to be upon us to. We're being called on, and we're going to have to deliver. It's a great time.
I want to ask you a final question, and there is a reception outside.
Okay, well, if I'm gonna.
Wait, here's my final question. You flashed by this life lessons slide.
Okay, I'll do that.
To close a talk with, as the oldest person in the room, I think you should give it.
Yes. Well, one of the things as an academic is some of my colleagues have been reluctant to give advice. And I love it. I love giving advice. So I love the title advisor. I'll tell you what you should do with your life. Sure. Let me know. And now that I've had a 40-year career, and maybe because now that I have the Turing Award, people care what I think now. So, all right. So
You're even more dangerous.
All right. Yes. So they might listen to me now. So for me, what worked well for me was I maximized personal happiness versus personal wealth. I think you grow up in America, you think those are the same thing. They're not. You know, there are very wealthy, unhappy people in this country, like our president. So, and I don't feel, and looking back at my career, well, like, what's wrong with personal happiness as a goal as opposed to, I can't figure out what's wrong with that. But think about that. Those aren't the same thing. Family first, I think, especially today, but it was even true when Ed and I were young. You know, as a professor, there's all these uses on, demands on your time, and it's very easy to put your family as lower priority because you want to make other people happy. So I didn't do that. I had time to think about it. It was going to be family first. So I have 2 sons, so it was Indian guides and Cub Scout leader and soccer coach and field trips and all that stuff. And so when your adorable young sons become rebellious teenagers, Dad, you were never here. It's Indian guides, Cub Scouts. You know, it was very satisfying. All right, you're around. And you really, I had a colleague who told me this late at one night. You really don't want to say what he said to me, you know, if I had to do it over again, I wish I'd spent more time with my kids. You do not want to ever have that thought in your time. For those of us, for Ed Lasowski, at a certain age, there's this song that went out that would just send shudders through the heart of fathers, and it's called Cats in a Cradle. And it talks, if you want, it was actually a poem that his wife gave him to kind of slap him around, and he put it to music. But it talks about how you miss these opportunities with your son, and I'll do it later, and then, you know, you're older, and then you say, hey, son, let's get together. And he said, well, you know, I'll see if I can find time for you, Dad. And it's like, whoa, this could happen, right? So passion and courage. You know, I like to think I'm an intellectual, you know, logical person, but I'm not. You know, I have to really believe what we're doing and swing for the fences. You know, we try and hit home runs. We don't bunt for singles. The courage part of it is, as I told you guys last time I was here, I was a wrestler in high school and college, so kind of ironically, the physical courage from wrestling is intellectual courage somehow in me. And I feel like if something's wrong, I have to stand up. So during the George W. Bush administration, there was a guy in charge of DARPA who I thought was screwing up, and Ed thought was screwing up, and wasn't funding computer science as like DARPA used to at the time. So he and I thought we should stand up to this guy, and no one else wanted to do that. But at that, you know, so I think we're both glad we did it, but, you know, there was some cost to that. This is advice I got from a senior colleague. And I think he was, given I was passionate and courage, I think he was warning me to be careful. And, you know, I've had a career to look back on, and this is true. You know, friends kind of come and go, like people you went to school with, you kind of lose touch. You know, enemies never forget. They don't forget that you're your enemy. So I think, as far as I know, I have 2 enemies. One of them's that guy who at DARPA, and then another guy in my field. But, you know, but I feel comfortable with the decisions that made them unhappy with me. But think about it, right? You know, when you make an enemy, it's an enemy for life. I've kind of, in my DNA, believe in winning as a team versus an individual. I really want my team to win. Quoting Fred Brooks, one of our heroes, is there's no losers on a winning team and no winners on a losing team. So no matter what you do in a winning team, you're kind of a winner. And I just, you know, I believe in that. I think it came from, for me, for wrestling, I had wrestling coaches in high school and college who believed that if we bonded as a team, we'd be more successful, even though it's an individual sport. And I absolutely think that's the way the world works. But I think if you had other analogies like, you know, drama or orchestra, working as a team is good. I think I'm good at seeking honest feedback and learning from it. Especially if an enemy, you send them your paper, they're going to tell you what they think, and you want to hear that early on. It's easy to avoid feedback. It's easy to avoid. So there's a corollary to that, as I reflect on my career, is somebody who thinks they're the smartest person in the room. And in my career, there's a guy in my field who thinks he's the smartest person in the room, and he's not a very popular guy. There was an Ivy League president who thought he was the smartest person in the room, and he was fired. There's the founders of Enron. They're convicted felons. And amazingly enough, my ex-brother-in-law's brother is a convicted felon. And all these guys thought they were the smartest in the room. What was the flaw? They weren't that smart? No, I think they were smart. I think the flaw is if you think the smartest person in the room and you have an idea, Why ask anybody else what your idea is? Because you're smarter than everybody else, so I'll just go ahead and do it. I know what I'm doing, right? And I think you make these terrible mistakes where you go to jail or you get fired. But in any case, for younger people, it just, if somebody, you hear somebody thinks they're smart, just run away, you know. One big thing at a time. I still can remember kind of waking up on a bright morning, and it was God spoke to me maybe 10 or so years into my career. And what he said was, it's not how many projects you start, it's how many you finish. And it seems obvious, but I was just struck with that. You know, as a professor, you kind of volunteer for lots of things, and it's up to you to control it. And after that hit me, I did one big thing at a time. So when Hennessy and I wrote our textbook, that was the one big thing. I do other little things, but that was the major thing you did. And so to get those done, and when I was president of ACM, that was the big thing I did. When I was the chair of the Richard Tapia conference to help that get going, that was a big thing. So I did one big thing at a time. But if you do one big thing at a time for 30 years, you get a lot of things done, right? And for a lot of people, they just try to do too much and they can't get them done. So I would think about that one. And then the final thing is I'm a natural-born optimist. And I have one more slide, and this is the most important slide of the day. This is something that you will remember, the next slide. But to set this up, I'm a natural-born optimist, and the example is when I was 16, I was dating an attractive girl, and at the time, I asked her to be exclusive, and we'd only gone on a couple dates, and she dated guys, older guys, and she was only 16, and she said to me, I asked her, would you go steady, is the phrase we use, and she said, well, Dave, I don't know how to say no. So me, as an optimist and a logical person, I don't know, yes, so great, and I hugged her. And so she said, in her mind, she said, well, I'll let this guy live later, but we've been married 52 years. So she may still let me down, but it hasn't happened. But if you've been married 52 years, people ask, what's your secret for a long marriage? And so I'm going to tell you the secret. So this is the 9 magic words. And it's not that hard, right? It's 9 words. It starts I, you, I. All right. And this is for both partners, okay? So the 9 magic words, I was wrong. You were right. I love you, right? Those are the 9 magic words for a long, happy relationship. There's no substitutions. I was wrong. You're a jerk. I hate you. That doesn't work. You got to say all the words. And it's not just for one gender here, not just for one sex. It's for both of these, and both have to say it. Okay, with that, I'm done.
Join us outside of the reception.